The first speaker is Chris Ormerod from Trobe University with this slide.
All right, first, you can all hear me? Yep. Okay, well, I'd like to first thank the organisers for organising such a wonderful meeting. There's a really good collection of mathematicians here, and it's a credit to the organisers. So I've changed my title a little bit, because what I really want to talk about is reductions from, well, what we all know as the lattice potential Korteweg de Vries, or H1, or whatever you want to call it, to the additive discrete Painlevé equation with E6-1 symmetry. And this is with the goal of actually looking at solutions. So how can we look at solutions from the lattice point of view? So what we're going to be trying to do, and we'll be successful, is we're going to look at a set of simple solutions of the lattice equation and how they map to the solutions of the discrete Painlevé equation. So this is, in this way, we're going to get some simple rational solutions through our correspondence, and we're going to get some hypergeometric solutions. This is directly from solutions of the lattice equation. Okay, so, I mean, there's a number of approaches to get special solutions. I mean, for example, you know, you can look at hypergeometric solutions just by plugging in a Riccati equation. I mean, that's a discrete Riccati, so that's a fractional linear transformation. So this was done, for example, by Grammaticos, Romani, Satsuma is in there. They also did the Riccati solutions to the particular equation that we're looking at today, and that was done in 2001 in their special solutions paper. Kajiwara also looked at how you get hypergeometric representations of these solutions, and this is directly from Riccati. There's also the bilinear framework. So this is a very powerful framework by the Japanese group. So there's Kajiwara, Normi, Yamada. They've looked at the hypergeometric solutions and determinantal solutions from QP4, for example. Kajiwara in his study of QP3. Then there's also the Pardeo approximation framework. So Yamada talked about that in this meeting as well. So Yamada talked about how you get lax pairs from this, and there are elliptic lax pairs. So in the recent paper, on the elliptic lax pair for the E8 Painlevé equation, this was inspired by the Pardeo approach. So separate from that, there's the orthogonal polynomial approach, and this is the approach adopted by Nick and I, and not just Nick and I. So also there's the work of Walter, Peter Clarkson. So this is where you look at moments, so you can get determinantal expressions for the solutions of Painlevé equations in terms of determinants of hypergeometric functions as moments of orthogonal polynomial ensembles. So, and then there's geometric approaches. Now that's very, very closely related to the direct approach, but really it looks at special configurations of the blow-up points and how you can use that to get when there is Riccati solutions. So there are a number of approaches. And what I want to talk to you today about is really what I would call a reductive approach. So that is, you get a set of reduced equations, you make a correspondence, but then you look at the solutions of the lattice equation and transfer them over to the discrete Painlevé equation. Okay, so, so this is the equation that we're going to be looking at, and it's been brought up today, so Anton talked about it before in this meeting. There's been a number of papers on the solutions. So now, why do I find this equation so interesting? Now, one of the things that I find very interesting about this equation is that it arises as two distinct forms of isomondromic deformation. So that is, in 2004, Arinkin and Borodin explained how this equation appears as a discrete isomondromic deformation, which is a connection-preserving deformation. But it also appears, and as we saw recently in this meeting, as a Schlesinger transformation, which is a discrete isomondromic deformation. So it's a classical differential, and I apologize for using the term differential in this discrete meeting, but it comes as a discrete isomondromic transformation of a monodromy problem. So that's kind of interesting. Another reason, again, I apologize for using a discrete equation, a continuous equation. It sits just above the sixth Painlevé equation. So this sixth Painlevé equation is also a nice equation. And I must admit that part of the reason I wanted to do this was I wanted to fail. So I want to see how far the additive, like how far I could go with H1. That is, could I get the entire discrete Painlevé, so additive type Painlevé equations from just H1? And I was 50% sure that I would fail in getting E6, but I actually was successful. But sometime I have to fail. So yeah, this I think there's this barrier that in going a little bit further, but anyway, that's another matter. Okay. So what are the equations that we're talking about? So lattice potential Korteweg de Vries, often known as H1, it's been brought up many times in this series of talks. So what I'm going to do is I'm going to basically take the lattice potential Korteweg de Vries, H1, and I'm going to impose a periodic constraint. So this here is a 4-2 reduction. That is, if you go across 4 and up 4, you set them to be equal. So this is a way of reducing the lattice equation, partial difference equation, to an ordinary difference equation. So what we're going to do is, what we're going to show is how particular solutions of the lattice equation are going to give us solutions of the reduction. That is, this is the reduction, how we're going, and these will include solutions of dp1. So there's a natural way of getting solutions of dp1 and lifting them up to this E6 equation. And there's solutions of dp4, which naturally lift up to the, this equation. So this is going to include rational hypergeometric. So this is the classic two special solutions that we're interested in. Okay, so we've really pioneered, well, not pioneered because there are many people who have done reductions, but looking at really lax representations of reduction. So, of course, reductions have been done for many times by many people in this room. For example, Frank, Nalini, Vasilis has done lots of reductions. But here we really establish a method of finding, in a mechanical way, lax representation for a non-autonomous reduction. So anyway, here what we do is we're going to specify an end direction. So specify a simple step, and every other step, so every other shift is going to be just a product of a simple step in our end direction. So here we're just labeling the points. We're labeling them in a certain way so that every single point W is either a W0 or a W1 with n shifted either positively or negatively. Okay, so in order for this reduction to make sense, so you've established periodicity. But in order for it to make sense, you need the equation at two distinct parts of your lattice to agree. In order for that to make sense, you have this constraint. Now, that constraint up there, so PL plus 4, when I move over 4 and I move up 4, it has to be the same equation that defines the evolution. So that means that I can shift all the things in, as functions of L on one side, shift all the functions of M on the other side, and what you get is a natural separation of variables. They have to be you get a constant that is in L and M. So that constant in this case is H. So that is PL plus 4 minus PL is H, and QM plus 2 minus QM is also H. Okay, so if you do that, then you've got a natural way of assigning variables. So this is just a period. So it's, you get H times by M over 2 plus some variable, and that variable is periodic. And similarly with the PL, so you get L times H over 4 plus some sort of periodic, yes? Oh, yes. Yes, you're right. Not all 0. all sorts of inconsistencies will apply. But yes, 1, 2, 3. Okay, that means that a shift in n. So a shift in n is actually a shift across one and up one. So that every shift in n is going to actually change our variable. So we're going to have to define a way of going from the periodic variable a1 to a2, and then a2 is going to go to a1. This is just this is all specified in our paper, our 2013 paper. Okay, so when you look at the evolution equations for the reduction, what you get are these. So this is just a simple application of our lattice potential Korteweg-de Vries. This has been done many, many times before. It's kind of nice, but this is your equation. Now so this is the reduction, and the other thing to notice, and what we'll be looking at later, is the fourth power of this mapping. Now the reason I choose the fourth power of this mapping is because when I move over 4, I actually have that the A1, A2, A3, A4, A5, and A6 are all constant under fourth powers of the mapping. That's very, very important. But they're not constant under single shifts. So we're going to wish to identify the fourth power of this mapping with the E6, additive E6 Painlevé equation. Okay, the first thing you can do. So H1 is defined in terms of differences. So you can define a difference. So I'm going to define U in terms of the difference of the W naughts and V as the difference in the W1s. Stock standard, many people have done this. So that means that you get a coupled system of equations that look like dP1. Right? So this here is already a fourth order system. We've gone from a sixth order system to a fourth order system. So the other thing, so this is a coupled version of dP1. So this is a way in which you could say that all the solutions of dP1 can map to a solution of dPE6. Okay, so the other thing to notice, I can actually solve this equation, this top equation in V. Right? So I can solve it, and what I get is that I have a way of just expressing this in terms of the U. Very, very simple. So I shove in my equation for V, and there I get an equation in U. Now that's still fourth order, but everything is in terms, so if I multiply that whole equation by U bar, I get something that's completely expressible in terms of ratios of U's. So that means that I can make this little substitution that nu is going to be U bar over U, and then I can get a third order system. So we've gone from sixths to fourth to third. Now the non-trivial thing to see after that is that this is there's an actual invariant. So it's a bit hard to see, but this can be written in the form of an invariant minus an upshifted, well, this minus something is equal to 0. So this defines an equation for D1. So this equation for D1 here, which determines our invariant, is a second order system, and it's in nu. So this is an equation for D1. So if you have a solution of the lattice equation, this is going to define a D1 for you. So this is the second order system. So remember, these AIs are supposed to be interpreted, they are supposed to be shifting in n, they're not constants in n, they also shift in n. So you have to remember that. And what we're going to be interested in is the fourth power of this mapping.
Sorry, Chris, is there something missing in the last denominator in the first equation?
No. In this part,
In the first equation, the last denominator on the left, it should be a quadratic problem.
B double bar times something.
B double bar.
Second line.
Oh, yeah, maybe. Well, it'll be right in the paper, don't worry. But B double. No, wait a minute. No, it's supposed to, no, that is correct. No.
B bar.
Yeah.
B bar?
B bar.
Okay. Yeah. Okay. There is supposed to be a V bar there. All right, anyway, let's proceed. Okay, let's proceed with the way in which we build our Black's representations from the theory that we built up in the paper with Reinhardt and Peter. So what you basically do is start with the lattice, the lax representation for H1, and you get an L and an M. So what we're going to be able to do is construct these matrices, which is going to shift a scalar variable, x, which we haven't specified yet, and n, well, we know what n is, in a particular way. So x here, I should say, is h times L over 4, and that means that we can construct A, which is going to basically relate two periodic points. So it's going to relate the point Lm with the point L plus 4, m plus 2. And you can do that by writing this A as a product of L's and M's in a particular way. So here we get, by writing the matrix as a product of L's and M's and replacing all the variables that we know with the reduced variables, this is how we get our lattice our representation of the reduced equation. So the compatibility between these two systems is just written there. So this is going to be our lax pair for our mu system. So this is the lax pair for the second order equation that we originally had. If you do the whole substitution for what W1 is in terms of U, and then U in terms of V, and then nu in terms of U's. Okay, so what are the properties of this matrix? First of all, in the x variable, it's degree 3, okay? And it's degree 3 in a very, very special way. The leading matrix, that is the matrix at A3, is actually just the identity. The other property is that the subleading, so the A2, is very, very nice. It's lower diagonal. Now, whenever you see that, you can say, well, I can do a gauge transformation to make that diagonal. Very, very simple. Because the leading matrix is the identity, so I can always transform the second. The other thing is that because I built my A matrix out of L's and M's, those L's and M's actually have a particular determinant. So the determinant of my A matrix is actually a product of the determinants of the L's and M's, which are actually very simple in the case of H1. That means I know exactly when the determinant is 0 in terms of the spectral variable x. Okay, so these properties should remind those in the know of Arinkin and Borodin's lax pair. This is exactly a copy of Arinkin and Borodin's lax pair. All we need to do is make the right parameterization of this A matrix in order to get a correspondence with the system that we had, the reduced system, and A6. So let's do that. So first of all, I'm going to provide an explicit parameterization of the Arinkin and Borodin lax pair. When I was a student long, long ago, well, not long ago, but anyway, I looked at this paper and I thought, it was too hard. But after a while, I thought, well, I can actually do this. I can get an explicit parameterization because it is actually buried in there. You just have to work out exactly what it should be. So this is a parameterization of the Arinkin and Borodin at lax pair. And all you need to do here is specify the y and the z variable. Everything else can be determined as functions of the y and the z once you specify it. So I've specified a y variable, which is the 0 of the 1, 2 entry, and the z variable, which appears when you substitute in the y as x, you get a diagonal matrix, and it's a specific combination of the multiplication of the two diagonal entries, which is supposed to be the determinant at y, and, well, it's just something that you need to try. So, of course, I say that this has to define the alpha, the beta, the gamma, well, have I used gamma? No, delta and epsilon, and this is just an explicit representation of these coefficients. So this here, you could actually leave this out as an exercise for the interested person who is in the audience. But yeah, this is just specified by those relations. Okay, so you know exactly what the parameterization is. That means you can draw up this correspondence. You've got this correspondence with the lax pair, which means you've got y in terms of the nu. But I figured that the actual expression for nu was so ugly that I couldn't dare show it to you, so I've got the expression here in terms of u and v. It's quite simple to go to the expression in terms of nu, it's just too ugly to show you. So you also have, so you've got y, you've got z plus y. So this is an explicit expression in correspondence between the lattice variables and the variables of the dPe6. So these solve this following equation where the tilde is interpreted as bar, 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 bar. So that's 4 shifts in n is equivalent to 1 shift in the tilde. So here, of course, so now we can jump to the part of the talk that we look at rational solutions. So what is the simplest case? What is the simplest case of H1 that we can solve? Well, what happens when we allow the QL to be simply linear and the QM to be simply linear as well? So this is the simplest case in which we can actually get a solution of the lattice potential Korteweg de Vries equation. So under these conditions, this is equivalent to letting the A1, A2, A3, A4, A5, A6 be given in this way. In this, if we do this, then our equations for u and v simplify dramatically. Okay? That means that when we shift this up, this equation remains unchanged. So we've gone from a way of getting something that was 4th order. It's in this choice of variables, it's back actually to just a simple evolution equation. So if you stare at this long enough, you could actually come up with a simple solution. One of the simple solutions is u is equal to a constant and v is linear. Now this is equivalent to letting our original lattice variables, so this is equivalent to letting u be linear in n, our w0 be linear in n, and our w1 be quadratic in n. So this is a simple solution of the lattice equation. When you allow your u and v to be this solution, what you can do is you can plug it in, see what your d1 should be, and then you plug it in and you get these values for y and z. So this here is a rather complicated but bona fide rational solution of the additive E6 equation. So yeah, and you can verify this quite easily just by shoving all your variables in. Okay, so another thing that's quite interesting, you can also swap the roles of u and v, and you get another rational solution. So this is just another rational solution. But what I find really interesting is actually you can use the Becklin transformations. The L and the M are actually also, you can think of it as more like a 3-dimensional consistency. That is that for every Becklin transformation of your lattice equation, you can manufacture a Becklin transformation. You can lift it up to the level of the ordinary difference equation. Some of the Becklin transformations are rather trivial, but some of them are non-trivial. So it's a bit of a light, well, these, the L and an M actually lifts to Schlesinger transformations of the associated linear problem. So basically you're lifting it up and you get another solution. If you manufacture it in a certain, manufacture the solution in a particular way, you can get a Becklin transformation. And so, for example, if I choose L, which shifts A1, and then lift it to a rational transformation of the associated linear problem, what I can get is actually another solution. So this is a way in which you can look at the 3-dimensional consistency as giving you an infinite family of rational solutions of the original ordinary difference equation. Okay, so you've got an infinite number of rational solutions. This is, of course, just an alternative approach from the affine-Weil transformations that the Japanese group has pioneered. This is more on the level of the linear problem. So that is that you get a seed solution and you get an infinite family, but just using Schlesinger transformations instead of affine-Weil transformations. Okay, Riccardi solutions. Of course, the Riccardi solutions were known in 2001 in the paper by Romani et al. So what we have is, all we do is we allow the y to vary in a certain way, and I don't know what that 3 is. That should be a sigma 3, but I probably mistyped it. And we allow our z to be, so this is just a fractional linear. What you do is you can shove in these fractional linears, see how, when the evolution corresponds, and you get y and z, and you can actually use this to, you can solve explicitly by aligning this with contiguity relations for certain known 3F21 formulas. So this was done by Kajiwara. So this is one way in which you can get explicit hypergeometric solutions of the original equation. Now, at the lattice, on the lattice case. The lattice case, so up here I've given you a formula in nu, which is second order. Except this here is actually, it's quite easy to write the Riccardi solutions for this equation as well. Now, this equation, you just know what nu is, you know what nu down is, because it's just a Mobius. So you can see, you can shove it in, and you get these equations. Okay, so you get a little bit of a different condition from what was seen by the original work of Romani, and you get this condition. This is 2D1 plus A1 plus A2 dot 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 dot. This is actually the same condition that Nick Witte gets when he looks at the orthogonal polynomial approach for the Riccardi solution, well, the hypergeometric solutions. This is slightly a different constraint. So this is, I think, it may be related in some way. I'm sure it's related in some way, but this has given me a different seed solution for my hypergeometric solutions of the Painlevé equation. So when you look at, so you've got a single shift, of course, fourth power of single shift is still going to be a linear problem. So it's still, you have this single linear equation for your nu, and you can solve that in terms of hypergeometric functions. So this is slightly a different. So this is still giving you hypergeometric functions, but from a very different standpoint. Okay, so the conclusions. So basically, we've given you reductions from the Schwarzian Korteweg de Vries all the way up to the QPE6. You can do that for any of the degenerations. So this method would also apply to the Q from the Schwarzian. And we'll also give you, for all the degenerations of the DPE6, you can get a similar sort of method to give you rational solutions as well. I was wondering, this is a bit provocative, could you use this, because this equation sits above P6, could you use some sort of limit to get a reduction from the potential Korteweg de Vries to P6? It's a little bit out there, but anyway, 50-50. Can reductions be done on a purely geometric level? So this is so some people have talked about this. So Adam Dolewa talked about doing it from a geometric level from the KP level. I'm wondering whether that could be done. And this is also related to the second point. Okay, so just on time. So this is a whole lot of references that I was sporadically throwing in the talk. Thank you.
Questions, please.
Norman?
My question is, or maybe it's a remark, it's about rational solution.
Yes.
And in case of Painlevé equations or discrete Painlevé equations, basically a way to get rational or algebraic solution is to look at the fixed point of the diagram automotive, the diagram. And I would expect your rational solution should corresponding to some fixed point of automorphism. Have you?
No, I haven't considered that. No.
Also,
No, this is this is a bit in its infancy.
and also, in the case of P6, the P6 spectrum transformation is just the D4 type case in Europe, where you are working on E6.
Yes.
And D4 case, rational solution corresponds to the so-called Memura polynomials in the case of Painlevé equations. And it has a very striking or remarkable combinatorial expression. And also, Masuda has already gave determinant representation. So there are determinant representation or very interesting combinatorial expression for this. So maybe someone could try to figure out this.
Yeah, that would be good. I think that needs to be done because at the moment I don't have determinantal expressions for my rational solutions, and they must exist. That maybe you could possibly obtain them through work that Jun and Ying-Chi are doing on the lattice equation level.
Yeah. So in the case of Masuda's, he uses a so-called determinant representation of universal character type.
Yes.
And so this your construction should also be related to Suda's UC hierarchy.
Yes.
So
It should be, but I haven't tried to. I've only been working on this about 2 months, so I haven't looked at exactly.
So your approach is directly related to UC hierarchy too.
Yeah, I would expect so.
I gave a comment instead of.
Further comments, observations? If not, thank you again.